Okay, so we are now towards the end of this section. Only a few exercises are left, and today we are going to solve all of them. And these last few are about yet another kind of representation of groups known as the coset representation, because it involves cosets of a subgroup of the given group. So before the exercises start, there is a small paragraph in the text, and the paragraph just says this. Say you have a group G and you have a subgroup H. Now in the discussion preceding this theorem 292, we have already come across this previously. We defined some functions Tg, right? Now these functions Tg give us a representation of G, just like previously those functions tau G gave us the permutation representation, the functions lambda G gave us the second permutation representation. So here also these functions Tg are going to give us a kind of representation. We are going to call that representation the coset representation of the group G by the subgroup H. But unlike the permutation representation, here we will not unfortunately be able to represent G isomorphically inside a permutation group, but homomorphically, not necessarily isomorphically. It may be isomorphical, you may find an actual copy of G inside the permutation group in which you are representing this group, but it may only be a homomorphic copy also. So let's start with this exercise. Here, what is our G? G is a cyclic group of order 8 with generator A, of course, which is an element of order 8 itself, and in it H is the subgroup generated by the fourth power of A. So that means because this original group will have order 8, so this will have order 2. So we have to find the coset representation of G by H for this G and this H. Now before we get to that, we would like to go back to the actual definition of Tg and what the actual representation is in this case. So let's do that first. That is, before writing the solution itself, let's recall those things. So here the setup is this. You have your group G, H is a subgroup of G, and S is the set of all right cosets of H in G. S itself may not be a group. In fact, it is a group if and only if H is normal in G. In this case, S is just the quotient group of G by H. But that's not the point. We are not going there. Instead, what we do, we consider for every element G in G a function Tg. You can compare this function Tg with those previous functions tau G, which is a function from G to itself. Here, however, this is a function from S into S, and so that means the input of this function is going to be a right coset of H in G, and the output is also going to be a right coset. And the precise definition of the function is this. Say Hx is coming from S, then evaluating Tg at Hx means having Hxg. So had this function been that tau G, you would have multiplied a group element from your original group by G from the right side. Okay, that's what that tau G function was or is. Here instead, because we are having a coset as input, we are multiplying that coset itself from the right side by g. So this Tg is somewhat like tau g, multiplication from the right side by the subscript group element. And it turns out that this Tg is in fact a bijection on S, and that is why each such Tg is an element in the permutation group of S. And this association between G and Tg gives rise to a function. That function is of course this, whose definition is just this. This is the coset representation of G by H because in the set S we are considering the right cosets of H, and that is why, because cosets are involved, this is called the coset representation of G by H. Okay, now let us start the solution. So in order to start the solution, we would of course have to know what the set S is for this G and this H. So that's where we start. So this is the solution to this one. The set of right cosets of H in G is S equal to, we call it S itself. It turns out that in this case it is just these four right cosets. HA, it's not difficult to see. HA, HA square and HA cube. So keep in mind that because we are after all doing what? We are going to find these functions Tg for every G coming from the original group. And already the theory says, or we have seen, that these functions Tg are going to be permutations of S, that is permutations of these four symbols. So in this case, whatever Tg we are going to find, that actually is going to be a permutation in the group S4, the symmetric group of degree 4. So that's why we write next. So we just have to find those permutations. In A of S, which is isomorphic to S4, the T functions turn out to be this. Te is going to be E, and T a to the power 4 also turns out to be equal to E. Keep in mind that we have written this, we have already written this kind of things for the original permutation representation, also for the second permutation representation, that is tau suffix E we wrote is E, lambda suffix E is also E, and in those equations we interpreted this E as the E coming from the original group G, and this E as the E in this group, that is the identity map on S, which is in fact the identity element in this group. Here also it's the same. Okay, so that is Te and Ta to the power 4. Next, it turns out that TA is the same as TA to the power 5, and just like those exercises, here also I urge you to actually do the calculation and verify what you see here is in fact what we should have. So it turns out to be this 4 cycle H, HA, HA square, HA cube. Now this particular one is rather easy to verify, especially this TA. What is TA? What will TA do? If you calculate the value of TA, the function TA at h, by the definition it will just be multiplying h from the right side by a. So h will become HA. That's what this this cycle is also doing. It maps h to HA. Then multiply HA from the right side by again a. So HA goes to HA square. HA square goes to HA cube. And HA cube will go to what? HA to the power 4. But because H is having A to the power 4 as its generator, so A to the power 4 belongs to A. So HA to the power 4 is actually equal to H. So that's why this gets mapped back to H. So we just simply, by looking at how things are going, we immediately see that yes, TA is this 4 cycle. But then just like that, you can of course verify that TA to the power 5 also will turn out to be this. So those parts you please do it. Next, we have TA square turns out to be the same as TA to the power 6, and it is this product of these two cycles. Times HA comma HA cube, and finally TA cube turns out to be equal to TA to the power 7, and that is again a 4 cycle. This 4 cycle, H goes to HA cube, which goes to HA square, and that goes to HA, and HA of course comes back to H. You can just randomly choose any one of these. Say you choose HA and apply on HA TA cube. That means what? Multiplying HA from the right side by A cube. That gives us HA to the power 4. That is equal to H. So yes, but randomly you can check like this. I want you to check everything. And that's it. We have covered all the elements of G. Keep in mind, G is the cyclic group generated by A, and it has order 8. So the elements in G are E, A square, A cube, A to the power 4, 5th power, 6th power, 7th power. There are 8 elements. So that's it. So the coset representation of G by H. By H, that I mean this way of saying this thing, this phrase takes into account H also. It tells us what the underlying subgroup is. So we should write this. G by H is the map theta from G into A of S, and A of S, just to see what A of S is, you can write that it is the same as S4, isomorphic to S4. and the definition of theta is going to be, of course, always just this. So that's the solution. Next, let G be the dihedral group. Of order 2n, where we know that n is a positive integer greater than 2. Those things are there, in the original definition of a dihedral group, so they are not repeated here. That is, the smallest value of n is 3, and as such the smallest dihedral group is of order 6. And it makes sense also because we already know that any group whose order is at most 5 is abelian, and dihedral groups are not abelian. Okay, so this is 2n generated by the elements A, B such that A square equals B to the power n, that equals the identity, and AB is B inverse A. So that means A is playing the role of a reflection, and B is playing the role of the smallest rotation through an angle 2 pi divided by n radians. Or originally how dihedral group was defined to us, there in place of A we wrote x, and in place of B we wrote y. That's it. And what is our H? Let H be this. Since A represents a reflection, and here itself you can see that A square is E, so this is a subgroup. This is a subgroup of our group G. Now for this group and this subgroup we have to find the coset representation of G by H. Okay, I know that the dihedral groups gave us tremendous trouble when we were trying to calculate the permutation representation and the second permutation representation. Here luckily it's not that difficult. So first we write the set of right cosets. H in G is, again, it turns out that it's just this H B square, so things go in that pattern, and you go till H B to the power n minus 1. Because if you take the next one, then you get H B to the power n. B to the power n is identity, so you get H back. So these are all the distinct triposets. In all of these things, you are being asked or requested to verify. These solutions, in a sense, actually are not complete. They just give you an idea of, or these are rather the gist of a complete solution. Many things have been left out, only what we ultimately find out that are being written. So in A of S, so how many elements do we see here? N. So A of S is going to be isomorphic to the group Sn, the symmetric group of degree n. So in A of S, which is isomorphic to Sn, so now we are going to write the T functions. And here T of, oh sorry, it's not B, it's this. It turns out that T for the group element B to the power I. So B to the power I is it represents a rotation, and you know that AB to the power I represents a reflection. So we do have all the elements here itself, but keeping in mind that T of B to the power I will be the same as T of AB to the power I as well, if those two exponents are same, I. And it turns out that this is just a power of this cycle. Minus 1. It's the ith power of the cycle, and where I of course satisfies this inequality. So that we get all the elements of our dihedral group. And that's just it, because we have in fact taken into account all elements, and for them we have calculated the T functions. That's it. So the coset representation of G by H is theta from G into A of S, which is isomorphic to Sn, and the definition of theta is just that G gets mapped onto Tg. Next, let G be the group of exercise 21. It is that thing, that group of quaternion units, thus E theta, A, B, C, theta A, theta B, theta C, that 8th order non-abelian group. And let so what is the subgroup here? And let H be this subgroup. Now from that exercise, from where this group arises, there itself we have seen that this is the center of the group, center of the group that we are considering here. So that itself is our subgroup. Find the coset representation of G by H. So coset representations don't seem as daunting as permutation representation or the second one, but of course that comes at the expense of having a homomorphic copy of G which is not necessarily isomorphic by H. Solution: the set of all right cosets of H in G is, okay, so here what the right cosets, so they are just simply this HA, HB and HC. So that means our functions TG here are all going to be elements in S4 essentially. So in A of S, which is isomorphic to S4, now the T functions, first of all, T of E is of course going to be E. T of theta is also going to be E. Next, TA, which is also the same as T theta A, is the product of these two transpositions, H comma HA, one transposition, and HB comma HC, the other transposition. Then TB turns out to be the same as T theta B, and this one also maintaining the symmetry is just yes, H, HB, HA, HC, and finally TC. Let me just simply write it, mimicking these things, and then let me verify if it's correct. Yes, of course. So the coset representation okay, this is S4. That's just it. And there is one more exercise. let G be Sn, the symmetric group of degree, and of course the author, yes, of course he would again write it, the symmetric group of degree n. The first couple of times it's okay to again write whatever you have written in symbol in words, so that you go through it 2 or 3 times, then you know for sure that this symbol represents this. But if you keep on doing this, it quickly becomes boring, and it defeats the purpose of having notation, so that we do not have to again and again write. But he goes on, acting as permutations on the set let H be the set of those permutations which fix the symbol n. And one can easily see that this H is actually a subgroup of G. And now there are 3 parts. In part A, we are asked to prove that H is isomorphic to the symmetric group Sn minus 1. Prove that it's not just any subgroup, but a subgroup that is isomorphic to Sn minus 1. Part B, find a set of elements in G such that the corresponding cosets of H give all the right cosets. That means this is the full list of all the right cosets. And the third one is the coset representation. Find the coset representation of G by H. So the first job is to show that H is isomorphic to Sn minus 1, and the task of that comes before that which is showing that H is itself a subgroup of G, is of course left to you, and it won't take much time or effort to see why that is so. Because you are in a finite group, you just have to take two elements of H and see that their composition again belongs to H. And before that, again, make sure that H is non-empty. Okay, so that's just it. Not going to say anything more than that. So we are going to directly produce one function that will be an isomorphism. Solution part A. One can show that the function, say, what should I call it? So phi from H into Sn minus 1 defined by sigma phi to be sigma 1 to up to n minus 1 is an isomorphism of H onto Sn minus 1. Now there are some things I should explain here. So what is H? H is the set of those elements in Sn which fix the symbol n, right? None of them changes n. When you input n, the output is also n. So such functions, they make up H. Now when you choose one such function, sigma, from H, keep in mind actually you are choosing a function in Sn. That means sigma is coming from Sn. So sigma maps this set into itself. And in fact, sigma is not any such function but a bijection of that kind. Do you remember this notation? Sigma, and in the below it you have a set which comes as a subscript. It represents the restriction of the function sigma to a subset of the domain, and that subset here is this subset. So the notation is the restriction of sigma to this subset. So that means this part, so that's just it in part A. You have to, it's left to you to prove that this claim is true, that this function indeed is, first of all, keep in mind, because the function is something we have defined, you have to first of all make sure that it's a well-defined function, no matter how trivial that is. and then you have to prove that it's a homomorphism, and also it's a one-to-one homomorphism. That makes it an isomorphism, and then it's onto as well. Keep in mind, in this book, isomorphism does not automatically mean onto. Isomorphism only means one-to-one. That is, injective homomorphisms are called isomorphism. For onto-ness, you have to again show it. So that's how H becomes isomorphic to Sn minus 1. Next, in part B, we have to find those representative elements that will give us a full set of all the right cosets of H in G. For that, we can write like this. You consider this n cycle. Let tau be this particular n cycle. Then of course tau is what? Tau after all is an element in Sn, right? So since tau is an element in Sn, so you can consider the right coset of H by tau. It makes sense, and in fact not just this right coset, we are going to consider a number of them, and they in fact are going to be all the right cosets of H in G. Since the index of H in G is equal to n. By the way, do you see how that is coming? Perhaps I should write one more step. This is by definition the order of G divided by the order of H. Now G being Sn has order just n factorial, but because just now we have proved that H is isomorphic to Sn minus 1, so they are going to have the same order. So that's why in the denominator you would have n minus 1 factorial. So this is going to be n, and that n is also the order of tau as an element in Sn, because tau is an n cycle, so its order is going to be n. So since we have this, and tau itself does not belong to H. Why? Because tau changes n. Tau does not keep n fixed, it maps n to 1. The following right cosets are all the right cosets of H in G, and they are these. Okay, so that's how those elements A1, A2 up to AN are just E tau square, all like this, all the way up to tau to the power n minus 1. So they give us all the right cosets of H in G, and here we do not actually have any repetition. You are in fact looking at distinct right cosets of H in G, which you can prove also. And now finally we come to the question of finding the coset representation. Unfortunately, here calculation of the functions Tg, that's all we have to in fact do that is in fact really what we should do when we are trying to find the coset representation of a group by some subgroup. But in this case, due to the general nature of the group, that is because n can be anything, I do not see how that can be in general found out. That depends on n generally. So instead, what I have written here is just simply this. But maybe I am not getting something which you may get. So let me first write and then I will discuss a little about it. So just simply as if I don't really understand what coset representation even means, I am going to write this. The coset representation of G by H is theta, which maps G into A of S. But what is S? The S is the set consisting of these right cosets. That's why we have been asked to find the distinct right cosets. And you can see that there are n elements here. Of course, after you prove or convince yourself that these are really distinct. So that's why this becomes isomorphic to Sn, because there are n symbols whose permutations we are considering in A of S. Oh, I need to write where S is the set of right cosets. Now, I end this thing with a remark. So you can see that we haven't actually calculated the functions Tg due to the general nature of n. It seems difficult to calculate the functions Tg for G belonging to G. So that is just my opinion about the situation, and I end things here with just this. But you are of course welcome to still think of it, and if you see something, and in fact let's just for a moment you try to think of why am I saying this. So what shall we need in order to calculate some such Tg? Say you try to calculate this, say. By definition of the function Tg, this is nothing but h tau square g, not forgetting that this g is in fact coming from Sn. But This is again going to be a right coset of H in G. So we know that this is going to be here somewhere, but which one? Is there really any way of knowing what ultimately this one will be without knowing what G is? And given how large the group Sn is and what different kinds of permutations we can have in Sn, G may be many different types of things. No? Say your n is 5, the permutation G, it's actually itself a permutation, right? The permutation G may be the identity permutation, it may be a 2 cycle, it may be a product of 2 disjoint 2 cycles, it may be a 3 cycle, it may be a 4 cycle, it may be a 5 cycle, who knows what it ultimately will be. And depending on all those things, you have to know what this right coset is. Now, if you are given some fixed value of n, then you may at least try to see what sort of things you would get. You can get at least some idea. But for general n, it seems almost impossible, to me at least. But still, if you feel that I am missing something, please let me know. So here the things end in this section. After this, there is of course the next section where we generally, okay. So in the next section we have it's titled Another Counting Principle. So there we see the this thing. Say you have a group G, you consider 2 elements G and H, then you form something called the conjugate of G by H, which is this element. So we will see what this element has to do with G and what comes out as a consequence of those considerations. So that's what we have in the next section. So we will see that in the next group theory update. And our next upload is this coming Friday. So today we have done groups. So Friday let's do what should we do? Fields. Let's go back to field theory, where we have started construction with straight edge and compass now. So let's see what comes after what we have so far done there. So with that, I wrap things up for tonight. So see you on Friday with field extensions. Until then, this is me, Lucifer, from A Mathematical Room. Have a nice day.